Good evening, everyone. It is our May Speakers Night 2024. Happy Aurora and welcome to Rask Toronto Center. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of the Rask Toronto Center, and this is our Speakers Night presentation. So please note that this meeting is in an online only presentation. We're not at the Ontario Science Center. Later on, our president, Tom Luton, will be talking about our various programs. But first, we have, of course, a very special event, that being the Speakers Night. Now, before we go ahead and kick off, I do want to just mention that this is the last speaker before the summer break. So if you really like to catch all the speakers you can, we'll be back Wednesday, the 18th of September, with the next speaker after this today. So, as usual, we'd like to go ahead and start off with a bit of a land acknowledgement. I'd like to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here, together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and Earth. So go ahead and welcome everyone. I'm very excited today because we have an amazing speaker to introduce. Tonight's speaker is none other than Maheen Hemani. She is a Bachelor of Science Honors Astrophysics student at York University, going into her final year. But of course, the reason I'm so excited to introduce her is, of course, she's also part of the LNI Carswell Observatory team since 2021, and if I may say so, one of the observatory's most experienced presenters. So you're in for a treat tonight. She has acquired research experience on several topics, including peculiar quasars and high redshift galaxies and JWST, James Webb Space Telescope, all during her undergraduate studies. She's currently working as a research assistant at York, not with myself, but with another professor, involved with dark matter research over the summer. She's got a wide range of interests and enjoys everything from astrophysics to philosophy, and I'm sure I'm not the only one who's excited and looking forward to hearing more. So, Maheen, please take it and us up, up, and away.
Thank you, Dr. Hyde, for the kind introduction. I really appreciate it. I'm really happy to be here tonight to be able to talk about galaxy quenching at high redshifts. It is a very interesting topic. I could be biased because I did research on it, but it is a very active area of research currently, which makes it a great treat to learn about this. So I'll start my talk with a bit of an outline. So I will start with introducing galaxy quenching. Within that, I will talk about galaxy formation, what are the current widely accepted theories. I'll link it to galaxy quenching so we better understand why it is important to understand galaxy quenching. I will then talk about the proposed causes of galaxy quenching based on cosmological simulations and what we can add to the simulations to make it make more sense. I will then talk about what cosmological simulations really are and how important they are for astronomers, astrophysicists, and cosmologists to be able to understand the formation of the universe. And lastly, I will talk about galaxy quenching with Thesan. So Thesan itself is a cosmological simulation. I will talk a little bit about it later in the talk. But this is what I've worked on during the past year, so I will link it to what my project was. So let's talk about galaxy quenching. What does it really mean? So before I do dive into the introduction, I did want to give a background on galaxy formation. So when thinking about galaxies, we often think about a very large number of stars that are bound together by gravity. But there's really more to it. It's not just stars that are bound together, but there's dust, gas, there's dark matter, and there's supermassive black holes at the centers of galaxy. And maybe the answers lie within those other parts of the galaxy about how galaxy formation happens. So we know that galaxy formation began soon after the Big Bang, but our understanding of how they ended up the way we see them today is somewhat limited. The most widely accepted theory of galaxy formation currently is the bottom up theory, also known as the hierarchical model, which is presented here, and I will talk a little bit about it. The idea is that the large scale structure of the universe was formed as a consequence of growth of primordial fluctuations, which was due to gravitational instabilities, which was very common during the early universe. The gravitational instabilities caused the gas clouds within the universe to collapse, forming extremely high mass stars. So the massive stars would then form clusters of stars, and of course, gas was within it as well. And this was about 10 to the power 6 times the mass of our sun. And these are known as proto-galaxies, which you can think of it as baby galaxies or young galaxies. So the reason that I compare it to the mass of the sun is that it's very common within astrophysics, you might know, to compare masses to the mass of the sun. So you will find that during my talk as well. The proto-galaxies usually would then merge to form bigger galaxies that we see today, and they're typically of masses 10 to the power 11 solar masses. So from that number difference, we can see that this suggests that they must have undergone numerous mergers to go from 10 to the power 6 mass of the sun to 10 to the power 11 solar mass. So galaxies would then eventually evolve, and in the case of this diagram, we see that there's two options. There's spiral galaxies or there's elliptical galaxies. So a spiral galaxy, we believe, would be a result of a galaxy evolving in relative isolation. From that, we mean that there's fewer interactions, and that is something we observe when we see the arms of a spiral galaxy, which is very gas heavy, and that suggests that there hasn't been as much star formation as there has been in the case of elliptical galaxies. So to construct a model that definitively explains galaxy formation, we need observations from not only recent but also early universe to agree with our theoretical simulations. And with galaxy quenching in the early universe, we are kind of looking at one aspect of this, as it is a big mystery when it comes to galaxy formation. Here you see an image of two galaxies merging together. We still observe galaxy merging within the universe, but it's just not as frequent as we expect that it was during the early universe. So things start to get more complex when we start to consider different other types of galaxies, as their distribution of mass, which means that their distribution of stars and dark matter then starts to differ. But we will not be diving too deep into how different galaxies make things more complex, but I did want to talk a little bit about what these galaxies are. So here are some examples of these different types of galaxies. Spiral galaxies, like our Milky Way, are rich in dust and gas, with stars still forming in their arms. Elliptical galaxies have used up all their gas. We also have lenticular galaxies and irregular galaxies, examples of which are Magellanic Cloud and Sagittarius Dwarf Galaxy. You'll also notice these photometric images. When I say photometric images, there's usually two kinds of data when it comes to astrophysics. So there's photometric data and then there's spectroscopic data. Photometric images are based more on the light that we receive from an object, whereas spectroscopic data is based on the wavelengths and different wavelengths that are being considered, and they're based on the chemical composition of the object. So here we're looking at photometric images, and these are 18 different small blue objects that are 11 billion years from Earth. And they're considered to be possibly be the seeds of some of today's galaxies. So each of these contains several billion stars, and their blue color suggests that these are very active. So this is also something to keep in mind for the talk today. Blue refers to active star formation, whereas red refers to non-active star formation. So this then takes us back to what we then believe according to the hierarchical model that we just discussed of clumps merging and colliding with each other to give us the massive and luminous galaxies that we see today, and which is an evidence of galactic evolution because the galaxies are not as we're observing them in the early universe today. So they've gone through some sort of evolutionary track to be the way they are today. So this is a good point to start talking about what galaxy quenching is. Quenching refers to a halt or a stop. And within this context, it suggests a halt in star formation. It is the transition of a galaxy from an active star forming phase to a quiet non star forming, or also known as passive phase. This diagram depicts exactly what I just said. If this quenching is permanent, we can interpret it as a galaxy in a way dying because it has stopped forming stars. Based on our discussion in the last slide, galaxies form from gas falling into the gravity of a dark matter halo and then collapsing into new stars, which is what we call the active stage of galaxy. When all of this gas is used up, galaxies die, which is the passive or non active stage of galaxy. That's pretty straightforward. But the question is, why exactly is galaxy quenching a problem in the early universe? There's multiple reasons to why we don't understand it properly um, because there are multiple things, but uh, the main thing that I want to mention is there is no reason for us to believe that all of the gas would be used up in the early universe when everything is hot and active. So there has to be some other reason for quenching at high redshifts. Because to say that a galaxy died so early in the universe is a big claim. And it's kind of a mystery. We don't know what mechanisms could cause them to quench. And some of them we observe that they're quenched and they're continually quenched till today, which is known as a state of quiescence. So they've been quenched since a very long time. So it is a mystery if they will go back onto star forming main sequence, which means will they again start forming stars after a big quenching period, or will they continue to be quenched for a long period of time? It is important to note that some studies and research have also pointed towards mini quenching. That is also within the early universe, and that is the case of temporary quenching, meaning that yes, galaxies stop forming stars for a while, but then they transition back into their active phase. And I will show everyone a plot that I made during my research, which will help us better understand what mini quenching is. So now on to observations. Of course, there is multitude of observations, but I wanted to show this one specifically because this is something I used as a reference during my research. As most of you might already know, with the launch of James Webb Space Telescope, we can now observe higher redshifts. What does that mean? So as a general reminder, higher the redshifts we are looking at, the earlier we are looking into the universe. So for example, if right now it has been 13.7 billion years since the Big Bang, then the way the scale of redshift is constructed, we're currently at redshift 0. And so redshift 5 would correspond to 1.186 billion years since the Big Bang. So in this image or plot, we're looking at a recently quenched galaxies only 700 million years after the Big Bang, which is a period of time in the history of the universe when everything was forming, like it was the formation of the first galaxies, the first stars. And to say that a galaxy is quenched during that time is confusing. So I wanted to set the scene by first us to be able to look at this observation, and then we can go into how our theoretical models are trying to make sense of this. So how exactly do we know from this data that a galaxy is experiencing quenching? The answer is star formation rate, or SFR for short. So a way you can think about this is, let's say a galaxy is a factory, where gas inflows into this factory and it forms stars. The higher the star formation rate, the more efficient and productive the galaxy is, and vice versa. So the plot in the right is taken from a recently published paper, I would say in 2021, and it contains details on the observation of this galaxy, which was quenched so early. And this plot shows that this galaxy star formation history, how it fits with different spectral fitting codes. Now, that is not as important to us right now. What is more important to us is to look at the activity of this galaxy. We see that the y-axis is showing a star formation rate in msun per year, whereas the x-axis is showing us the look-back time in million years. So look-back time refers to the time we're looking back in time. I think that's pretty self-explanatory. But the point is that if you're starting at a specific redshift, you want to look back in time to the Big Bang or to a higher redshift. So we're going from a redshift of 7.3 to a redshift of 9.3. And here we see that all of these spectral fitting codes show us that the star formation rate of this galaxy is 0 when it is observed. And it was quenched about almost 20 million years before the point of observation. And so this is a big evidence of quenching being observed. So now that we have a little bit of an understanding of what galaxy quenching exactly is, let's talk about what causes galaxy quenching, or at least what we think causes galaxy quenching. So this is a great explanation of possible causes of galaxy quenching. This has been adapted from a paper that I have listed here. If anyone's interested in a good summary of what we know about galaxy quenching up till now, this is a good paper to look at. But theoretically speaking, some non-feedback mechanisms can also explain galaxy quenching. And we need to note that a galaxy could have one or more of these processes going on to maintain a state of quiescence. So to be permanently quenched, we might need more than one of these to explain whatever is happening within a galaxy. So I will explain all of these a little bit. I'll first start off with just pointing them out. So some of these reasons that are mentioned here are gas not accreting onto a galaxy, a gas not cooling, cold gas not forming stars, so a gas being too cold, cold gas being rapidly consumed, so non-efficient consumption, and then the removal of gas. And the pointers below these are just showing the reasons that could cause all of these mechanisms to happen. So first, let's talk about what does it mean for a gas to not accrete on a galaxy. So this is to say that massive galaxies may quench due to reduced gas accretion onto their dark matter halos, which is known as cosmological starvation in more official terms. Something to keep in mind here is that even if there is no gas accretion, of course, a galaxy is undergoing stellar evolution. So the gas that is produced could still further induce star formation. So this can, of course, not be the only reason why a galaxy is permanently quenched or going through a long period of quiescence. Secondly, the second reason of why a galaxy could be quenched is a gas not cooling enough. So for galaxy formation to happen, we need the gas to be at a specific temperature. If it is too hot, stars will not form, and if it is too cold, stars will not form. So in this case, we're saying that the gas is too hot, which is to say that for galaxies with masses greater than 10 to the power 12 solar masses, some of these processes become very prevalent. And these processes cause the gas to heat up too much. And if they don't cool down, they cannot form, it cannot collapse and it cannot form stars. And of course, in general, in the universe, there's a lot going on. So a galaxy is not isolated. It's not just the galaxy itself. There's a lot surrounding it. So to avoid all of this happening can be difficult, and of course it happens. So this is one of the reasons why we could observe quenching within a galaxy. Thirdly, is cold gas not being able to form stars efficiently. So quenching can also be due to low star formation efficiency instead of just absence of fuel. So it isn't that there isn't enough gas, it's that the efficiency is low. So for star formation, the cold gas within the galaxy needs to lose its kinetic energy. Certain non-thermal processes within the galaxy can cause an injection of kinetic energy, making it harder for the gas to settle and taking too long. And some of these processes that can cause this to happen is morphological quenching, bar quenching, AGN feedback, and magnetic fields. The fourth mechanism that I want to talk about is cold gas being rapidly consumed. This is the idea that if cold gas is consumed by galaxies faster than it is replenished, there will be a period of quiescence due to a lack of fuel. This can happen if star formation takes place in efficient bursts triggered by compressive gas motions and effective angular momentum loss. So in certain galaxies, the gases are just used up very efficiently. They form stars very, very quickly. They use up all of their fuel, and it doesn't get enough time to replenish its fuel from the production of stars. And that could cause a momentarily period of quenching. The fourth mechanism is the fifth mechanism, and the last one that I'll talk about is gas being removed. So accretion onto supermassive black holes could release sufficient energy and momentum to remove gas from galaxies. Now, how does that happen? Essentially, some galaxies have active galactic nuclei in their centers. So most galaxies have supermassive black holes. But what is AGN? AGN is the case when gases accrete onto this supermassive black hole, and because of gravity, they rotate around the black hole and it becomes extremely hot. So it produces a lot of energy and it is very luminous. And the most luminous form of these AGNs are known as quasars. So this case where there's a lot of energy being released is known as the quasar mode feedback. And it is most efficiently triggered by major mergers, so galaxies merging together, which causes a lot of gas to inflow. So rare and short-lived, but it can remove gas supply from massive galaxies, so causing quenching. So I hope this gave a little bit of a summary of what's happening. You'll notice that the main thing is gas, right? If there's enough gas, is it at high temperature? Is it being removed? Is it being added? What are the mechanisms that are adding gas or removing gas? So that's I would say, the major idea. Of course, there's a lot of physics behind it, but in general terms, that's the idea when it comes to quenching. So now let's talk about quenching and cosmological simulations. I'll give a little bit of an introduction on what they really are. So as one can imagine, astrophysical processes are not only complex, but the study of universe has its limitations in terms of observations. We're dealing with large distances, we have limitations in our technology on how far we can see. So cosmological simulations have been instrumental in the advancement of our understanding of structure and galaxy formation in the universe. Simulations allow us to model a variety of physical processes over an enormous range of scales while following a non-linear evolution of galaxies. So the better our understanding of the physics, of course, and which is associated with the universe, and our computing methods, we can reproduce a large number of observed galaxy properties. We can use them to test widely accepted as well as alternative cosmological models and see which one works better with our observations, which is eventually our goal. These are some visual representations of some recent structure and galaxy formation simulations. So the simulation I've worked on during my research was Thesan, which is the illustrious TNG simulation framework combined with some other things. This is the illustrious TNG simulation visually, and it was combined with some other physical processes which are important to consider, such as self-consistent radiation transport, non-equilibrium heating and cooling, etc. So the main point I'm trying to make here is there's a lot of physics that goes behind these simulations, and that is what we need to better. So the better our computational methods, the better our physics, the better will be our simulations. But it's just a great way to have this predictive model that can help us see what maybe we cannot for now directly see in the early universe. And it should help us understand the structure and galaxy formation within the universe, which is eventually a big goal for astrophysicists. So, um, I also wanted to talk about the underlying cosmological model, which I think everyone should just have an idea about. So, from observations, we know that universe is geometrically flat. It is dominated by dark matter and dark energy, which comprises 95% of universe's energy density, and only 5% of this density is made up by the standard model physics. Now I can't emphasize this enough, but to say that the everything that we see around us is only 5% of the universe's density is crazy, but that's true. So this model suggests that dark matter, which is a big part of energy density of the universe, it is cold, it has negligible random motions when decoupled from other matter, and it is collisionless. The lambda within the Lambda-CDM model represents dark energy, which suggests that the universe is not only expanding, it is undergoing an accelerated expansion. So it's expanding faster and faster. Here is like a quick summary image of what Lambda-CDM model predicts about the universe and how it came into being. So based on our cosmological simulations, our underlying cosmological model, which is Lambda-CDM, does not really satisfy our observations when it comes to galaxy quenching. So as you can see in this plot, this is a galaxy luminosity function, which essentially maps out how the luminosity is varying within intervals. The theory, which is the CDM model, is the red line, whereas the observations are the blue line. And you see the gap within these observations and theory. So in order for us to be able to fill this gap, researchers have tried including many of the quenching mechanisms that we discussed earlier within the simulations. And of course, this is currently a very active area of research. So far, research suggests that by accounting for supernova feedback in low mass galaxies and AGN feedback in high mass galaxies, we could fill in this so-called gap in theory and observations. And that's what this image is showing, that we're accounting for supernova and AGN feedback for different masses, and maybe we can fill this gap up and sort of have an alignment between our observation and our theory. But it's not 100% that this can completely do that. So you might be thinking about what these feedbacks really are, and why could they be useful in explaining galaxy quenching. So let's talk about it. They're not very different from the mechanisms we discussed earlier, except that their origin is a little bit different than what we talked about. So supernova feedback has to do with gas influx within the interstellar medium due to supernova explosions of stars within galaxies, which happen when a star dies. So when a star dies, which is what we call it goes supernova, it produces a lot of energy. And so this a lot of this energy, if that star is within the galaxy, it also produces a lot of gas and a lot of energy, a lot of heat, a lot of temperature. So how does that affect whatever's happening within the galaxy? It imposes thermal energy into the interstellar medium, and it suppresses star formation. Since, as we talked about before, stars cannot form if the gas is too hot. So the result is temporary quenching within the galaxy in question. This is more prominent in low mass galaxies than high mass galaxies. And the reason for that is just because of the scale of a supernova and how much energy it can really impart in the space around it. Stars don't go supernova that often, so when they do, it will be more prominent within the low mass galaxy than the high mass galaxy. What is more prominent in the high mass galaxies is the AGN feedback. This is a very similar mechanism to what we discussed earlier with quasar mode feedback. But the energy that is released by AGNs, as I mentioned before and explained a little bit about what AGN is, but the type of energy that it produces is in the form of radiation winds or radioplasma jets. And it, of course, has an impact on the surrounding interstellar medium. What this does is it causes negative feedback and it prevents gas in and around galaxies from cooling enough. It also removes and redistributes gas by driving massive outflows. The plot here shows that star forming objects have a starburst age of about 150 to 300 million years, while the most common starburst age for the transition region objects is around 300 to 500 million years. So this scale is in billion years, and we're talking in million years, so there's a bit of a conversion. But the peak AGN phase seems to occur roughly 500,000 years after the starburst. So that is to say that if there is quenching 500,000 years after the starburst of the galaxy, then that could mean that if there's also peak AGN phase during that time, that is exactly what is causing this quenching to happen in the first place. So this is sort of an evidence to how AGN feedback can cause quenching. So now I'll move on to the last part of my presentation today, which is galaxy quenching with Thesan. This is what I worked on over the past year. So I'll start with some introduction of what Thesan is. I did slightly touch on it before. It is a project that consists of large volume radiations and their hydrodynamic simulations. From a numerical perspective, it produces higher resolution than previous simulations of comparable volume and employs galaxy formation models that we know to give us the results we expect from observations down to the present day universe. Essentially, it includes many things that we talked about before. As part of the galaxy formation model, it uses such as the feedback from supernova explosions, stellar winds in the form of kinetic and thermal energy, black hole formation, growth, and feedback, to mention a few. The primary goal of Thesan is to investigate the connection between galaxies and the intergalactic medium through the epoch of reionization. The epoch of reionization is a period in the history of the universe when neutral hydrogen ionized into protons and electrons, likely as a result of the arrival of the first stars and galaxies, before which the universe was dark and filled with dense primordial gas. If you want to dive deeper into the details of the simulation, the website is on the side as well. I really liked this diagram that they've put on their website to explain cosmological simulations, sort of like a something you're inputting the physics into, and you're getting the realistic universe out of the tap, kind of. So this is a great explanation, or a visual way to understand what numerical simulations really are. So let's talk a little bit about some of the plots. These are the plots of some of the results from the work that I did. Um, Here you're seeing two different plots at two different redshifts. This is a way to find out the quenched galaxies within the data set that we were using. So we were working with 8 million galaxies, so 8 million subhalos, and from that we're trying to find which ones are quenched. Um, and this is sort of the approach that we used, and there were a couple of steps before this as well, but this is kind of like a result of galaxy quenching. So here you see the two plots. The y-axis is the change in star formation rate, and the x-axis is the mass of the stars, the stellar mass of the galaxy in the units of solar mass. And the redshifts are different. I already mentioned that. But here, what we did was we figured out the difference in star formation rate by fitting our star formation rate to a best fit line. And once we knew what threshold it kind of should lie below, we knew that below this cutoff, all of the subhalos are quenched. Because, as I mentioned before, the quenching has to do with the star formation rate. And so this is sort of like there's differences in the threshold that different people use, but this is something that we used also based on another paper. And you see here that anything that lies below this dashed line, which is the minus 0.75 dex, are quenched subhalos. In the lower redshift case, we see a galaxy quenching in low mass as well as high mass subhalos, but there's none in intermediate mass subhalos. Whereas in the case of the redshift of 7.32, we only see quenching in the low mass subhalos. There is no high mass um, quenching. And you might wonder why that's the case. So although we haven't used the simulations to look into it, but one of the reasons we can actually think about is we can connect it to what we discussed earlier. So when we're talking about lower redshifts and we're talking about quenching in low mass and high mass, if there is a supernova feedback in low mass halos, then of course they're going to undergo quenching. And if there is AGN feedback, then high mass halos are going to undergo quenching. But there's no intermediate mass halos that are undergoing quenching. Why? That could be because for the intermediate case, the supernova feedback is not strong enough, and AGN feedback is not strong enough because the black holes within the center of those galaxies are not big enough because of their size. So that neither of the two mechanisms that we were talking about earlier could explain quenching within intermediate mass galaxies. Whereas on the right, we're talking about redshift of 7.32, which is a higher redshift. So we're talking about even earlier universe. The galaxies are not big enough to have enough AGN feedback quenching. So there's only quenching in low mass so early on in the universe. So a way in which we can further explore this quenching is to talk about star formation histories. These histories essentially tell us the activity of the galaxy over a specific period of time. So the two plots are of galaxies of different masses at the redshift of 5.51. So this is about 10 to the power 6 solar mass, and this is a much higher mass galaxy, so it's about 10 to the power 10 solar mass. And both of these galaxies are coming from this plot. One of them is from this region, and one of them is from this region. So these histories tell us the activity of a galaxy over a period, and the two plots are of different masses. One is higher, one is lower, and it appears that the one on the left is of mass about 10 to the power 10 solar masses, and you can see how its star formation rate continues to increase up to a certain point. And then it starts to drop. So there's a sudden drop, which means that it underwent quenching. And we don't see it going back up. So it could be that this is temporarily quenched, although we cannot tell until we have more data to see if this galaxy is quenched in lower redshift. So if we're looking at 5.51 and we see the signs of quenching happening even before, then is it still quenched? The only way to know is to check more data. On the case of the right-hand side, this is what I was telling everyone about earlier during my talk, the mini quenching or the temporary quenching. This is particularly interesting. You see how the star formation rate drops, then it's constant, so it's 0 for a while, so a few 100 million years. Then it goes back up, and then it stays at this 0.02 star formation rate for a while, then it goes down again, and then it's 0 again, and then it goes back up. So this is what we call mini quenching. And this is something I think is more explainable because we could say all of those mechanisms sort of happening, such as AGN feedback and other mechanisms that we discussed of why things became temporarily quenched. But then, of course, with star formation and star evolution, they again started forming stars due to the gas that is produced. So lastly, I want to compare the star formation history of the galaxy identified by the James Webb Space Telescope with a similar galaxy we plotted. So the left plot is observational and refers to the star formation history as inferred from 4 different full spectral fitting codes. So this is the one that we talked about earlier. And this is what the observation is. And what we did was we plotted the same thing for this a very similar mass at a similar redshift with Thesan. So to see if the simulation is agreeing with our observations. And we looked more at the prospector spectral fitting code, and that is because of how the star formation rate is distributed. These are about 40 MSIN per year, so they weren't comparable at that higher star formation rate value. So one more thing to look on the left plot is that here we're referring to the look back time, whereas here we're going since the Big Bang to the redshift under consideration. So it's sort of like a flipped plot instead of the same plot being reproduced. So we're kind of doing it in the opposite direction. And to be able to further really have any kind of conclusion on whether it 100% agrees with our observations, we would have to dig deeper and do more research on this. But for now, it seems like, okay, we are observing quenching within the simulation as well at the same redshift. So that's a good place to start, right? We are seeing quenching within the simulation, within our theory, just as an observation. So that was pretty much all for the data that I wanted to show with Thesan. I do want to end off with some key takeaways so that hopefully everyone can remember some of what I talked about today. So what is the theory of galaxy formation, which is widely accepted? It is the bottom-up theory or the hierarchical model, which says clumps of gas merge together, bigger galaxies. Secondly, galaxy quenching refers to halted star formation. So a galaxy, when it goes from active phase to passive phase, star forming to non-star forming, then it is undergoing quenching. Thirdly, there is an observation and theory gap in our Lambda-CDM model and what we observe now with James Webb Space Telescope. However, accounting for quenching mechanisms within models maybe could fill this gap. What instrument would be used to be able to get a better understanding? Cosmological simulations. We need to advance our cosmological simulations and we need better data, which now we have James Webb. So the future is looking bright. We can look more earlier in the universe, so hopefully our answer is very close. This is an active area of research, as I said, and I am looking forward to us being able to find the answer. And that is it from my side. I hope you guys enjoyed my talk. Thank you.
Thank you very much, Maheen. It was great to get you back. Of course, it did take a couple tries, but I would say it was well worth it. Thank you for hanging in there and, of course, finishing the talk today. We're going to go ahead and pass to YouTube for any questions from the listeners over on YouTube.
The first question is from Zapfan. Zapfan, I thought the maximum star formation was 10 billion years ago. Was it actually earlier?
Yeah, that's an interesting question. So, maximum star formation, or the case of cosmic dawn, was actually much earlier. So it was the first billion year after the Big Bang. So the 1 billion year after the Big Bang, it actually started about 500 million years and then continued on. So no, it was much earlier than that actually.
The second question is from Swanita13. How did you get into studying this topic?
So for the topic, I've always been interested in cosmology in general. So galaxy formation has been something I've been interested in. I am an astrophysics major, so I am trying to explore different topics and see what I want to further study. And so when I had this opportunity, I was able to study it through Explore, which is a program that is offered at York. It is a research-based team of international universities collaborating together. And so this was one of the topics that they offered, which was galaxy quenching at high redshifts. And when I saw how active this area is and how we really need to know the answers, I really wanted to get into it and explore more.
Thank you everybody for your questions. We really appreciate them, and we'll make sure to pass those on to our speaker directly. Unfortunately, we are about out of time, so we're going to go ahead and pass off to our final transfer and say thank you once again to Maheen Hemani for hanging out with us tonight. Galaxies is one of my personal favorite topics, so thank you very much for covering that. And we'll go ahead and hand over now to the president of Toronto Centre, Rask, Tom Luton, to finish off the evening. Over to you, Tom.
All right. Well, thank you very much. And thank you very much to our speaker and to everyone who's joined us here this evening. Hopefully, I'm coming through all right. So, anyway, let's get on to our announcements. So, for those of you joining us live, this is one of two types of meetings that we have here on YouTube. You've just seen one of our speaker nights, and then in 2 weeks' time is going to be one of our recreational astronomy nights. For those of you who are joining us in the YouTube chat, please say hello. Please enter some questions for presenters, as others have already done. If you're a new member of the Toronto Centre, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. So our next recreational astronomy night is on the 5th of June, 7:30 p.m., both live on YouTube and in person at the Ontario Science Centre. The sky this month, we're still looking for a presenter. Then David Pluskowskis, I apologize, I've probably mangled that name. We'll be talking about the eclipse at Six Nations. And then I'm going to be talking about eclipse chasing, a long day at Long Point. So join us either in person at the Ontario Science Centre or live here on YouTube. And as Elena said already earlier, this is our last speakers night for the season. We're about to start our summer break. So our next speakers night will be in September, and we hope you'll join us then. Coming up on Saturday, the 1st of June at 2 p.m., we will be having a celebration of life for our good friend Blake Nancaro at the EC Carr Astronomical Observatory on Blue Mountain. There's going to be some solar and evening observing, weather permitting, opportunities to share remembrance of Blake, rocket launches, and a potluck barbecue dinner. Be advised there's a rain date of June the 8th. Attendance is by registration only and is limited to 100 attendees. However, if you can't make it, the program will be live streamed on Rask Toronto's YouTube channel for those who can't make it. We'll be providing the link for you on our website to sign up. We'd love to see you. Also happening on the 1st of June is solar observing at the Ontario Science Centre from 10 a.m. to 12 p.m. Rask volunteers will be setting up filtered telescopes in the plaza area and offering views of sunspots and prominences, such as the fairly large sunspot that gave us all this wonderful aurora activity over the weekend. This is a weather dependent event, so please check our website for the go no go call before heading out. City star parties. So we haven't had much luck so far. However, we still got one more night this week, which is Thursday night at Baby Village Park on the 16th. From 8 p.m. to 11 p.m. As always, it's a go no go decision, so please keep an eye on our website. And then coming up on Friday night on the 17th at Millennium Square in Pickering from 6 p.m. to 11 p.m. Please join us for an evening of free public stargazing on the North Shore of Lake Ontario. Take a look at the moon and the stars through our telescopes, check out the astronomy literature at our info booth, and ask us some questions to learn more about the stars and planets. You can bring your own scope, and we're happy to help you set it up and aim it at the moon. Just remember that it's cooler down by the lake. And check our website for a go no go decision based on the weather before heading out. DDO going on at the David Dunlop Observatory this month. Saturday, May the 18th is Astronomy Family Night. Registration fee as shown here, and to register online, the links are at raskto.ca. Then coming up, the first clear night between May 21st and 23rd is DDO Stargazing Night, starting at sunset. Bring your own binoculars, no registration required, just walk on in. Friday, May 24th, 9:30 to 11:30 p.m. at the DDO is Astronomy Family Night. Registration fees are as shown, and links at raskto.ca. Planetarium Day for little astronomers is on May 25th, Saturday at 11:30 a.m. Again, registration fees and links at restio.ca. And then that afternoon, May 25th, starting at 1 o'clock, is Planetarium Day with registration fees as shown here. Links again, restio.ca. And wrapping things up, Sunday, May 26th at 12:30 is Sunday sun gazing. Fees and registration links again on the website. The CAO is open. We are still running some pre-pandemic, we're still running some pandemic restrictions. The main one being that only two unrelated persons are allowed to share a bedroom, and those are people who mutually agree to share said room. Masking in common areas is encouraged, but the preference of the people present will be taken. Public outreach events have resumed, and as have supervised weekends. So please take a look at the CAO bookings page for all the details before you make your reservation. Just a reminder, the Toronto Centre runs on clean, renewable volunteer energy. So if you're a Rask Toronto Centre member, if you're interested in helping out, if you've got any free time, contact the volunteer at raskto.ca. Just to highlight some of the things we're looking for, we are looking for a volunteer committee chair, marketing committee chair, and committee members. EPO committee is always looking for additional help with online presenters and telescope camera operators for virtual star parties. Reminder that in order to volunteer, you first must be a member. Just pointing out that Rask Toronto Centre has signed up with Benevity to receive charitable donations. So if you are a volunteer and your employer has signed up to make contributions for charitable work, please let us know at either president@rastio.ca or treasurer at rastio.ca. This is the part where I get to plug Rask membership. You can renew or sign up online at secure.rask.ca. Gift memberships are also available. Contact the national office at mempub@rask.ca. And finally, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all the forms of social media that we've got listed here. If you've been watching us live and you like what you saw, please like and subscribe and click the notification bell. Be safe and keep looking up. Good night, everybody.